start with this first speaker. Our first speaker is Professor Maria Amudio. She's a full professor at the University of Foggia, Italy, in the Department of Science of Agriculture, Food, Natural Resource, and Engineering Education. She graduated for her PhD in the same university, and Professor Maria Amudio also performed teaching in bachelor, master, and PhD degree in the same university. About the research interests, Professor Maria Amudio has a research interest in non-destructive technology for assessment of fresh fruits and vegetable quality, low-impact technology to extend the shelf life of fresh fruits and vegetables. If you're ready, can we start now? All right.
Good morning. Thank you to everybody, but particularly thanks to the organizing committee, to the Faculty of Agriculture, to the Dean for inviting me, and also for supporting me in all the travel, and everything was just perfect. So many thanks to everybody. Also thanks for giving me the opportunity to be the first speaker. So I hope I will make a good job today. As you know, just let me try the pointer if it's working. Okay, maybe, okay, I need some time. Today I will talk about recent advances in non-destructive quality evaluation and authentication of fruit and vegetable. As you know, I work, as it has been said, I work on post-harvest technology, but in the last year I focused more and more on this kind of technology. But we are a group in Italy, in Foggia, working on post-harvest, so storage of fresh fruit and vegetable and minimally processing, particularly fresh cut product. So what we care is the shelf life of our product. But how we assess shelf life, how we assess quality, we have many conventional methods to assess quality, but nowadays there is a growing interest in non-destructive quality evaluation. Moreover, quality, the concept of quality has changed over the last year. We were used to speak about sensorial quality, organoleptic quality, so taste, appearance of our product. We cared about this in the last year, but the consumer nowadays is becoming more and more interested in knowing nutritional content of the crops, and also now we pay a lot of attention to other things like labor condition or sustainability, so environmental impact of our methods on the crop. So when today I will give this overview, which is not just assessing quality parameter, but knowing a little bit more about the history of the product. Why non-destructive? Why we want to shift to non-destructive when possible? Because of course, being non-destructive, you save your sample, and in this way you can make more measures even on the same samples, or you don't have to choose when you are making a process, you don't have to choose on which sample to make your measurements. So generally we took some representative fruits of all the lot, while in this case we can have individual measurements of each fruit if we need. In the same times, on the same fruits, we can also measure more things. This depends on the model we are able to build. As long as we have model for many parameters, all these parameters can be predicted with just one reading. So we have real-time results, and what is more important, we don't need specialized personnel, we don't need particular instrumentation. Of course we need some instruments, but it's not like having a chemical laboratory. We don't need to prepare our sample, so we save reagent costs, but also we don't have to to take care of this reagent after using. And moreover, these measurements are reliable and consistent. Today I will speak particularly about optical method. We shift from computer vision to spectroscopy and then to hyperspectral imaging. So I will speak particularly of these two and what this optical technique do. They measure the interaction of a light source, of electromagnetic source with an object. And you know, when a light source hits an object, it gets mostly absorbed, it gets scattered, reflected, of course. We have specular reflectance, diffusive reflectance, and also eventually transmitted, and this depends on the fluids. For liquid, the transmission is very important. For solid, it's less important, but still we'll have different information if we measure reflectance or transmission. And we can arrange the setup of the light source and the detector depending on what we want to measure. If we are interested on transmission, reflectance, or even transflectance, which is taking back also the transmitted light together with the reflected light. The simplest, as I said, the computer vision system is the simplest and is, of course, having information on the visible reflected light. And it's the easiest way to use cameras already on the lines because it has been used for different aim like calibration, grading. So we can see by computer vision, of course, what is visible on the external surface of our product. So after calibration and graded by color, we added more algorithms predicting, for instance, size, or shape, defects. But of course, we cannot see what is internally by this technique. Just as an example, this is a study which tried to correlate from the image to give back the quality level. So these authors quantified five different quality levels from 1 to 5, and they are able by the image to see this quality level. And also they discriminate leaves according to cultivation practice. So this is an example how computer vision might be further implemented for other quality assessment. While if we go to spectroscopy, here we have the interaction with light. Generally, in this application, we use near-infrared spectroscopy, but we can have also visible or other UV, other lights. And particularly, what we get is what we call the fingerprint of the product, because the reflection, which is conversely related to absorbance, is related to first externally the morphology, which is contributing a lot to the scattering, of course for the particle size, also for temperature, many external factor, but particularly for the chemical composition. So each crop has its particular fingerprints, which in near infrared is also due to this molecular absorption of some boundary like CH and HOH, which are consist of overtones and combination bands. So we have a signal which is sometimes overlapping because we have many molecules vibrating at the same times. We know that there are some peaks characteristic of some compounds, but the elaboration is not very straight. It's not like saying, okay, at this wavelength I'm saying sugars and this wavelength I say phenolics. We have to use multivariate approach to deconvolute the signal and having information about internal characteristics. Hyperspectral images is merging conventional imaging with spectroscopy, and what it does, what we have, like when we speak about hyperspectral image, is a stack. We call it hypercubes. And hypercubes is a stack of images, one image for each wavelength. So if our spectral resolution, depending on our spectral resolution, we can have many images, hundreds of images, so one image for each wavelength, and particularly for each pixel, then we are able to have the mean spectrum. So you can work on this mean spectra, pixel by pixel, or you can select your object and extract the mean spectra. You can work on single image because we have pointer. But okay, I'm afraid to use pointer. But we have this hypercube with an and if we are interested in single wavelength image, we can work on that. And generally, we use also a single image, for instance, to threshold our image and to have our object of interest. Regarding the acquisition, we can go point by point, we can go by line, and by line acquisition is generally useful when you are in conveyor belt, so the conveyor is moving and you acquire line by line. And that's all. So what we can see with these techniques, we can see, of course, what is inside. In the last year, there are many instruments have been developed. They are portable instruments to go on the field. There are instruments, as I said, for online sorting. And if besides a conventional camera, RGB camera, you add spectral information, you may know what is inside. We know that fruits and vegetables are mainly constituted by water, but after water, the main constituents are sugar and acidity and acids. So this one are for sure the constituent you can see better than others. Water is overlapping a little bit the signals, but we developed a very good model for the prediction of maturity index. So this is our commercial application we can find online, we can find on the market. While latest studies concentrated on the prediction of phytonutrients, and since, as I said, water is the big part of it, and here we are speaking about few milligrams per 100 gram of product, is much more difficult to get the information. But latest study we did, in this study we were able to predict, for instance, phenolics content, antioxidant activity. In this case, I'm showing artichokes. This is a work we did on goji berry. Actually, Daniel Fachuraman is my PhD student, just got his PhD. And he came from this university to University of Foggia. And so in his thesis, he worked a lot with goji berry. Actually, he worked also on many other crops, but the thesis focused on goji berry. And here we can see prediction of ascorbic acid and the total phenolics of goji. This is having this model on the main spectra, so we may know online the content of vitamin in this case, or sugar, we also did, fruit by fruits. And so the color here is a color map, is indicating the concentration of the constituents. But as I said, we have also hyperspectral imaging. Actually, goji berry was already an example of hyperspectral imaging, but you can use hyperspectral imaging in different way. When in that case, in goji, I show you the average value of sugar, for instance, for a single fruit, but we can go inside the fruits and we know where exactly a constituent is located. If you think to pharmaceutical, you may know very well where a compound is located, and if the process went well, the mixture is okay. But in fruits, we can have concentration map. This is an example of rocket leaves. So pixel by pixel, you can have the vitamin C content. This is grapes, phenolics on grapes. You can see different concentration on the berries and on the rachis. This is the distribution of sugars within a slice of fresh cut. This is a fresh cut fennels. I don't know if you are familiar with fennels. I will show you later something. So this is the distribution of sugar. So you can see that sugar are concentrated in the internal part more than on external. So there is a gradient of sugar. And also you see the telematic vessels. We who had a higher concentration of sugars. In addition, we can know something else. So what's going on our product? For instance, we might be able to know about physiological problems and if we are able to detect physiological problem before it becomes too late, we can make, correction in our post-harvest chain to minimize post-harvest loss. So we can adapt protocols based on this. And when some example of physiological product, for instance, this is chilling injury in eggplants. We stored the eggplants at 2 temperatures, 2 degrees and 12 degrees, and so already after 3 days, we got some, oh, okay, now it seems it's work. It's working,
work.
but I don't know where it's, okay, but it's not really visible there. Maybe it's too far away. Yeah, maybe it's too far away. That's why. And so we could see the occurrence of chilling injuries already after 3 days, and depending on the algorithm, we could have a good separation of chilled and non-chilled product over time of storage. Still on eggplants, another study. In this study, we did like an ANOVA. It's a simultaneous ANOVA on all the spectrum, so on all the reading on the wavelength, in order to know the significance of the factor, the interaction, and also which wavelength were particularly affected by that factor. So the red one are the wavelength significantly affected by temperature or by time. So we could discriminate fluids stored at different temperature in blue and red in this score plot. And then, so this is the results of the discrimination. Also, we did the other study on green peppers, and we were able to detect also in this case chilling injuries. Another application, a different application, also Daniel helped in this study. He did most of the work. We used fluorescence imaging to discriminate mature green from immature green tomatoes. So when tomatoes are green, it's very hard to see if we can harvest, so they will further ripen when off the plant or not. So in fact, in the pictures after 12 days, 18 degrees, you can see that some tomato did not ripen, and we were able to discriminate so mature green from immature green tomatoes. This is an example of discrimination of common defect in loquat fruits made in cooperation of our group and University and Spain University and Research Center IVIA. The approach was to discriminate first 2 classes, and then so defects and non-defects, internal and external defects, and then all the kind of defects. Sometimes we care about discrimination of particular defects, but what is generally important is that we are able to discriminate defective fruits from not defective fruits. And this is another example from Daniel's thesis, which is about discrimination of 3 different defects on goji berry, black spot, mold, and visual damage. And particularly for small fruit, it's very useful to have an automatic method to make this selection, because when they are on conveyor belt, doing manually, it will be sometimes impossible. Even if you have a slow speed, maybe the sides on the defects is the other one. And this study, we were able to discriminate sound and defective very well, based on, what's happened? Based on sounds picture. So this, just using the spectra of the sounds tissue closer to the defects, we were able to discriminate sounds and defective fruits. While when we try to discriminate by 4 classes, sound, mild, moderate, and severe defects, the discrimination was, of course, a little bit lower. What else we can do? We also used this technique as an authentication tool, as a way to discriminate product according, for instance, to varieties, to time of harvest, but also to cultural practices. And for instance, in this case, I'm showing you the discrimination of 2 cultivar of artichokes. One of these has become in the last years also a protected origin varieties, so we discriminate 100% the two varieties. We also discriminate with a very good performance harvest time for this for artichokes. So we had 7 harvest time and we discriminated very well. This is fennel. I show you before the distribution map of the sugars. So also in this study, we discriminated among different harvests. And actually, there were 7 harvests, but doing one by one was giving lower performance. But grouping different harvests like harvest 1, 2, and 3, 4, and 5, 6, 7 could give 94 non-error rates. The same on grapes, we could discriminate 5 harvest time. And this is an interesting work where we discriminated 3 cultural practices, 1 conventional and 2 organic. The organics differed because in the conventionalized, it was let's say a conventional organic system where grower just substitute chemical with or fertilizer with a allowed one. So it's more similar to conventional, but you use what is allowed by the certification, because we know that organic certification is a wide framework, and you can do many different things inside that. While in the agroecological approach, there was more attention to the organic sources, so they used organic sources for fertilization, so to increase the fertility of the soil. They did these things in the same way, just changing this input, and the discrimination was very high, not only organic to conventional, but also within the 2 kind of organic system. Sorry, I don't know if I said tomato, these were strawberries. I don't know if I did, if I said a different one, because also we did something like this in tomatoes. In these last years, we got this project, which is sustaining low impact practice in horticulture through a non-destructive approach to provide, if I can have some water. To provide more information on fresh produce history and quality. So the aim of this project is that we are implementing, agronomists are implementing low input practice, LEAP, we call it LEAP, with a positive impact on the product quality, and we are trying to use a non-destructive tool for quality assessment and discrimination of this cultural practice. So in this way, we think we can support the diffusion of the low impact practice, and and also some marketing strategies in order to positively enhance the diffusion of this technique. We applied this on rocket and on tomato. So for instance, here you can see we have 2 different approach for irrigation, one conventional, so it's time-based, and one sensor-based, which is optimized depending of the needing of the plant, and we have a sensor to measure it. Fertilization, we have 2 levels, low and high, so resulting in 4 treatment, and you can see the discrimination of the 4 treatment. We did more or less the same things on tomato, but in this case we used 2 varieties. One was an autumn-winter cycle, and one was a spring-summer cycles. So over 2 seasons, 2 varieties, and also in one we applied the good water, and in another experiment we had brackish water. So the treatment were 3: open cycle, closed cycle with recirculation, and sensor-based nutrient solution. So in the sensor-based, the nutrient solution was adapted to the need of the plant. In the closed system with the recirculation, for instance, where there was some sensor of water content and also some conductivity sensors. So when saline, for instance, the saline concentration was too high, they recirculated the water. So the water use efficiencies of this system actually, depending on the water we use, and so the two experiment was different. And because when you use, for instance, saline water, so brackish water, you had a very high recirculation in the closed systems, and so the performance actually were similar to the open cycle. While when we use good water, things were different. In this study also we are trying to predict internal constituents like sugar, pH, acidity, ascorbic acid, and carotenes. And when we did different, the discrimination for each experiment of the three classes, and then depending on the similarity on the classes also by group, with sometimes a very good accuracy. But what is interesting is that we measured all the sampled in the same data sets, and we classify the tomatoes according to the water use efficiency. So actually, over the two experiments, we realized we had three different levels, low, medium, and high level of water use efficiency, and merging together the data, we only using, I think they were in green, 16 wavelengths, we could have 90% accuracy in the discrimination. And actually the further studies is now, in addition to discrimination, for rocket leaves, we are doing an experiment with 6 different levels of water use and efficiency, so we can see if we can predict the sustainability of the process. Finally, last part is on shelf life prediction. So for instance, this is an example of quinoa sprouts where, making conventional measurements is very hard because it's a product you cannot manage very well. You cannot put a colorimeter to measure color. And this is just an example of applying 3 oxygen level over time. And also in this case, we did an ASCA, so a simultaneous ANOVA, for the spectral information, and we could see that oxygen was not significant, the storage time was significantly affecting the...
Professor Amudio, you have 5 more minutes, if you probably can speed up.
Si, I'm almost done. This is classification of artichokes by days after cutting, so 0, 2, 5, and 7 days after cutting, and you can see 80 or 87% of non-error rate when we measured 0, 2, and higher than 5. Thank you. I show already something on green pepper, and also in this case we can predict the days of storage at 4 degrees. This is the prediction of shelf life for rocket leaf. We did prediction based on the initial quality attributes, so mesophilic, chlorophyll content, and also we did the prediction of the shelf life, so the storability of the product just based on the spectra we got at the beginning, at the time 0, and we actually got a very good prediction model. And as final example, we can use, even on conventional, I will tell you something more about predicting with this method conventionally attributes and shelf life. So we know that shelf life is the result of many changes in quality attributes. Sometimes you just focus on the most critical quality attributes which is affecting shelf life. While in this multivariate approach, you can use all the quality attributes at the same time. So you can model quality change by, for instance, in this work on lettuce, using a PCA, which is done on all the quality attributes. Then you model the effect of time, because you will see over time that a change on due to the time, so a change of the samples based on time and the variation of main quality attributes. And so this is a conventional approach with different quality attributes of fresh cut lettuce, and we did also the same, just with information of Wisnir spectra. So we had 121 variable fitted by PCN, and then the PC score related to time were fitted with linear kinetics, and we got the prediction of the shelf life, because then you can set up a cutoff criteria and determine the shelf life. So going to conclusion, we know that high quality is a key factor in the vegetable sector, but also that the concept of quality has evolved a lot in the recent decades. Non-destructive quality evaluation are becoming more and more relevant, but further research in these fields should be focused on, for instance, simplifying existing method, exploiting the possibility of predicting other phytonutrients, or to apply this model on over a large species or minor crops, for instance. We know that the adoption of sustainable practice can be considered a part of the broader concept of quality. And as I showed you, non-destructive method might be a tool to increase also information on produce history, so on cultural practice, and support then consumer choice. Thanks a lot for the attention. This is our Facebook page.
Before I start, I want to introduce Professor Renato Andrin Villano. Professor Renato Andrin Villano is a professor in economics at the University of New England, Australia. More specific in business school, Faculty of Science, Agriculture, Business, and Law. His area of expertise are on applied econometrics, agricultural economics, and development. Current research undertakings include the efficiency of productivity analysis in agriculture, education, and local government. He's also actively involved in government-funded research for development projects in Asia and Africa. For the sessions, he will be giving a talk with the topics about understanding from household decision-making to increase productivity through behavioral profiling, insights and implication for intervention design. Professor Rene, are you ready?
I am ready.
All right, if you're ready, I'll pass it to you.
Okay, can you hear me clearly?
Yeah.
Can you hear me clearly?
Yeah, I can hear quite clearly.
All right, okay.
Right.
All right, thank you very much, Mr. Chairman, and good morning, everyone. Selamat pagi, Ibu-Ibu Bapak. For your information, saya orang Pilipin tetapi tinggal di sini Australia for 32 tahun. I am very happy to be invited to be one of your speakers in this very good conference, and I'm really pleased to be sharing some thoughts to you. I wish I could be there in person, but as you know, travel restrictions still in place. But hopefully at the end of this talk, I would have shared something.
Maybe next time, Professor.
Conference.
Yeah, maybe next time
right.
we can invite you to come to the country.
Yes, we'll do.
Yeah.
All right. My talk today is actually going to be a little bit of a twist. I'm coming from a social science perspective. And I am going to be talking about some thoughts about understanding technology adoption, especially with the decision-making process of farmers. With the intention of improving productivity. But I will be looking at that from the behavioral lens. My area is basically from a social science perspective, agriculture economics, and most of the work that I do are actually along these lines. So My focus of the talk is actually looking at this, and one of the main reasons for doing so is because, as we know, there are so many technologies that have been developed that are intended for our smallholder farmers. But the question remains as to why some of these technologies are actually not adopted or well adopted by the end users. So what to expect today? I will provide a brief motivation and introduction, and I will give an example using the work that we do and what I do, and hopefully provide some insights from a behavioral lens in terms of designing interventions. I would like you to join the kangaroo to jump all the way to the conference logo towards the end. So when you can see that, then that means I'm nearly done with my talk. All right, so basically what we have here is to say that most of you, or like most of you, for example, a lot of us are engaged in many research projects, many research activities, whether it's international or local, research for development projects. Most of these projects, I'm pretty sure, are aimed towards improving the productivity or livelihood of smallholder farmers. And central to these undertakings are basically farm-level studies to generate knowledge and information on farmers' needs and identify policy options that would support rapid adoption and diffusion of technologies. What we do here is the core activity is basically we collect data from farmers, we analyze them, we examine their household resources, their perceptions, their adoption patterns, and so on and so forth, using some sort of a combination of a lot of modeling. But despite this being the focus of many studies and literatures in the past, there remains to be a question about, which is actually for us, development practitioners, scientists, and academicians, for us to bring the farmer's perspective into the forefront of our core business, that is technology generation and dissemination. So this is actually where I'm coming from. And also I heard during the opening ceremonies the importance of this conference. And that is precisely so, that there are many reasons why we are undertaking this task. What are the relevance of our activities? First, as we know, population pressure is continuing to increase. And hence the challenge of providing more food in the table, especially in the developing world, will remain a fundamental business for all stakeholders. Second, climate change has brought many challenges that resulted to averting some of the activities or some of the initiatives in order to avert some of the areas that will address these poverty issues. There are many public and private partnerships that have strengthened to increase their productivity, but there remains to be some questions whether these are widely accepted by our key stakeholders. The third issue is the farming systems innovation encompassing new technologies, farm management practices, marketing arrangements are being introduced to many regions to bid in order to increase productivity and, of course, to improve the livelihood of farmers. Despite these many efforts, as I have indicated in the past, the uptake and impacts of those introduced innovation have been variable and low outside the immediate impact, immediate program areas, even if there are evidence or demonstrated potential benefits to improve productivity, profitability, and farm household incomes. This varying income, this varying adoption or adaptation of innovation are actually common to some of the innovations that have been implemented in the past. One of those examples is the use of integrated crop management. As we all know, the ICM is a holistic approach to sustainable development. The aim of the integrated crop management is basically to enhance the quantity and quality of crop production. This technique of the integrated crop management involves other techniques such as rice cultivation, including integrated nutrient management and integrated pest management. These techniques will improve the efficiency of applying fertilizer, for example, and pesticides and so on. And that also considering some of the human health dimension. There have been some evidence of the success of this technology. However, there are also evidence of disadoption. So I would like to highlight the word that there are some evidence of disadoption, and so therefore we need to consider what that may be the case. Another example in Southeast Asia, case number 2 here, we have an example of a knowledge-intensive management for systems-oriented innovation, such as the Sustainable Resilient Farming System, or SRSFI. The Sustainable Farming Systems Innovation actually aims to reduce poverty by making smallholder agriculture more productive, more profitable, and resilient. And the core principle of this innovation is the conservation agriculture-based sustainable intensification. Again, there are evidence of benefits of economically and environmentally potential benefits of this innovation, but there are also varying levels of adoption across the different countries in the Eastern Gangetic Plains, for example. There are also a number of production and market-based innovations in other parts of the world, such as Indonesia or South Africa. This is an area that I'm directly involved. I have a project in Indonesia, of which this is a situation where we have an integrated crop-based livestock production systems. There are innovations, these are innovations that are aimed towards increasing profitability, productivity, and sustainability of the smallholder farmers. And this is based on the existing practices, tools, and technologies that are available to smallholder farmers. And then our main intention is actually to improve the supply of beef by increasing cattle numbers and slaughter way up at the smallholder level. And we have a similar project in South Africa, whereby we have the high value beef partnerships. This is an integrated production and market-based innovations, targeting smallholders with a view of targeting high-end market with free-range beef. Again, these are just some of the many examples of technologies or innovations or practices that we have introduced, that has been introduced to smallholder farmers. Regardless of the context of the innovations of where they are introduced, it is imperative that we understand how these are to be adopted and adapted by our end users. And for this context, I'm using the smallholder farmers as an example. Now, whether it is a production, process, or marketing, or process-based innovation, the success remains a big challenge for us all. The decisions made by farm households are central to the uptake of this particular technologies or farm systems innovations. The adoption and adaptation of new technologies and subsequent performance on smallholder farms will depend critically on the farm management made by farm households. Our farmers, whether they are men and women farmers, they will make decisions on a day-to-day basis that would affect the farm and also the household. So therefore, because they are interlinked, the decisions made about the farm will also affect the household or vice versa. Therefore, an in-depth understanding of the farm household decision-making will allow us to establish a platform for the development of appropriate and relevant and timely intervention. So that's basically our main goal here. In the past, or for several decades, the farm household decision analysis has been the central focus of many empirical studies. And there are varying frameworks that has been considered. And some of those frameworks here are basically including the ones that I have on the slide that actually points into several factors that allows us to consider the drivers of innovation and how it actually affects the main outcome variables, such as performance, productivity, poverty, or welfare. So as we can see, we have a number of factors to consider, and we have a number of innovations to consider. But despite this evidence, there are still some questions that remains, and some of those questions are already answered or can be answered or has been answered in some of what we know in the literature. The adoption literature, as you know, is massive. There are many, many published papers in the adoption literature. And some of the points that are highlighted in this literature are summarized in what I have in the slides here. This is actually saying that adoption, if we are to analyze adoption process, it is imperative that we should analyze the adoption process. As an economist myself, for example, we assume that the decision-making process is instantaneous. However, adoption is actually a multi-stage process, including awareness, trial evaluation, adoption, revision, or even to this adoption. So it is very much important for us to consider those different stages when we're considering adoption. There has been an emphasis on heterogeneity, meaning there has been an emphasis on understanding the differences between the potential users of technology based on their socioeconomic and biophysical realities, and of course, based on the technology being considered. There has also been an emphasis on learning and the role of social network. Several studies have already described and discussed considering new technology. Well, farmers will start with high degree of uncertainty, but there will take some process of learning. So there's some learning process that would take to reduce that uncertainty. And that would actually be highlighted and emphasize the role of social network and learning in order to avert some of those uncertainty. A diversity of scales and time, there are several studies that have been conducted in many areas of the world in different times. And because these are done in different times in period, there are several conclusions that we could come up with, and they are very much location specific. And one of the other strong focus of the existing literature is actually the strong focus of multidisciplinary nature. Meaning, if we develop the technology, there has been a very much a multi and interdisciplinary effort in order to develop an effective policy framework to enhance adoption, and that will require us a deeper understanding of the science behind this, behind the technologies, and of course, of the other dimensions as institutional or environmental aspects. All right, what are some of the methodological issues about this? We need to emphasize not only about the technology per se being adopted, but examine the nature and characteristics and features of the technology per se. There is a need for us to look at some of the roles of what we could do in terms of the role of social network. And also, we also have to understand the decision-making process of the farmers, going beyond profit. Farmers may decide to adopt a technology, not necessarily because of the profit maximizing behavior, but because of other factors. And of course, it is also important for us to consider, other than just explaining adoption, other just explaining the determinants of adoption, it is imperative for us to be able to predict adoption. By being able to predict production or adoption will allow us to enable to design an appropriate framework, whether it's policy or extension, that will foster adoption by smallholder farmers in the developing world. All right, despite what we have in the literature, there are still a lot of them that we can still do, and a lot that we can still add in understanding those behavior and decision-making process. When predicting and explaining adoption, we need to consider which matters most are the adopters of the technology. Do we consider the characteristics of the technology versus the adopters? And of course, how do we take into account the sociocultural and behavioral factors? In order to contribute into this, what we are going to look for, what I'm going to demonstrate to you, is the role of behavioral profiling. The role of behavioral and psychological profiling in order to understand some of these intricacies and complexities in the decision-making process. And I would just like to start off with a brief introduction of bridging the gap, the importance of behavioral economics. A classical farm household decision analysis is based on the assumption of economic utility maximization. However, as I've indicated before, there are some failures in the neoclassical economics to fully explain the individual choices that prompted consideration of individual farmers. So one of the approach that can bridge this is to actually use the behavioral economics which would combine multiple disciplines such as social sciences, economics, and psychology through the work of agricultural extension personnel. The behavioral economics will focus broadly on unpacking the black box of human decision-making process and explore the human dimension. So the human cognition in the manner in which tastes and preferences will form and drive the decision-making process. And the intersection of behavioral economics and adoption research will actually provide us insights into farmer behavior that will validate underlying behavioral models or call for improvements in those that are already existing or something that are to be developed. In order to consider behavioral aspects in terms of farm decision-making process, we have some of the themes that we need to consider as far as farmers are concerned. For example, some of the themes, these include but not limited to status quo. This is the tendency of farmers to just make a decision to stick to the status quo or to the default option. When we talk about cognitive bias, it is a systematic deviation from the rational decision-making due to the influence or context of and framing of the information that they received. And of course, we have the decision inertia, loss aversion, the tendency of the decision maker to attach more value to loss than an equal-sized gain. And of course, I have there the social influence, the extent to which the decision maker is influenced by social or cultural factors such as norms that will prevent or may support their decision. And of course, the last one is altruistic behavior. It is the moral practice of looking after the concerns of other human being or environment than oneself. So these are some of the behavioral themes that we can consider in terms of embedding behavioral aspect in understanding decision-making process. One of the approaches that we can do is actually behavioral profiling. And based on this, based on the underlying theories and themes, one of the first steps that we could do is actually to examine the patterns of similarities and differences among farmers. We can use what we call behavioral or psychological profiling. Essentially, this profiling is used in order to design, target, and evaluate intervention or preferred learning style that will enable farmers to improve their performance and increase adoption of technologies, increase adoption of process and tools, and of course, to achieve a broad scale of specifically designed interventions that are targeted towards the smallholder farmers. Now, it is another reasons why it is important to conduct profile of farmers. It is important for us to identify the key behaviors that are important and bottleneck in disseminating the technologies. As we know, we can understand through behavioral profiling, reducing or eliminating destructive behaviors. It
Professor
will promote,
Professor Rene, you
yes?
have 5 more minutes.
Yes, that's all right.
Yeah.
And then basically, some of these are basically can be considered in terms of behavioral profiling. The behavioral profiling is governed by a lot of theories in behavior, as I said here, on attitudes and social norms, behavioral control, and self-efficacy. Those are the themes. And this is actually governed by the behavioral wheels, of which it is actually divided into 3 areas of a dimension. The green is measuring about the capability of farmers and motivation and the opportunity. The red one would reflect the intervention functions, and the outer one will reflect the policy categories or intervention, or including communications. I would like to provide an example of this behavioral profiling into 2 contexts. Based on the example that I had mentioned, the Farm Behavior Project in Bangladesh, of which we have interviewed 746 farmers, and also in South Africa, where we interviewed 435 farmers. Again, the main objective of this is to basically obtain behavioral profile of farmers so that we can identify appropriate intervention. What have we done? So in order to do this, we've used a behavioral science-informed instrument to interview farmers based on the theories, based on the things that I have indicated. We've used multivariate and latent profile analysis in order to summarize the data that combine the behavioral profiles that allow us to examine the patterns of similarity and differences. The behavioral profiling instruments includes the following dimensions, as I have already flagged when I mentioned a while ago about the different behavioral themes. Some of the results that we have based on our behavioral profiling, this is the context of Bangladesh in terms of adoption of system conservation agriculture. We're basically able to group farmers according to behavioral aspects. And in this case, if I may just take you through to some of the things that of the variables here, these are considering the self-efficacy and so on. And as we can see, there are three distinct groups that we have here: Profile 1, Profile 2, and Profile 3. So Profile 1, who are these farmers? Basically, these are the ones that are majority of the farmers, they are the ones who are low in everything. However, they are continuing to understand and continue to seek information about the benefits of the technology. And profile number 2, these are the those that are in between. They believe that they have the capability to do things, but they are precluded from having not having some social support, so therefore they can adopt the technology. And of course, profile number 3, those are the innovators, positive-minded. They are all positive in everything. They have so strong social support. So as we can see, we are able to disentangle and be able to classify farmers accordingly. How about in South Africa? We also have 3 distinct features or group of farmers according to their behavior. The ones that we have in South Africa focus mostly on personality of farmers, being open, being conscious, and agreeableness. Those are some of the things that we consider. And we've separated the things for farmers, poultry and livestock farmers in beef, and we have 3 distinct information also. And of course, similar interpretation as what I have in the previous context as in Bangladesh, which means profile number 3 are the ones who are confident about their ability to succeed. They are the innovators. They are the ones who are open to innovations. So what are the implications for intervention here? Of course, persuasion, the messaging. How do we package the framing of our messages to farmers? Some of the examples of the intervention could be nudging. We could probably provide incentives through micro-incentives or pre-commitment. The role of social proof and education and training are imperative in advancing and accelerating the adoption of technology. When we are designing intervention, it's important, what are we targeting? Are we targeting the physical capability, psychological or physical opportunity? So those are the things that we need to consider when we design intervention. And intervention should have all the key characteristics such as affordability, practicability, effectiveness, acceptability, side effects, and equity for all sector or appease. And finally, some of the things that we need to consider based on the behavioral profiling, we are able to have increased knowledge and understanding about the benefits of our technology. It can be done through education and training. We can examine and evaluate the role of information or communication to improve the positive-minded.
Assalamualaikum warahmatullahi wabarakatuh. Selamat siang. Good morning. Dear participant, first of all, I would like to thank to the seminar organizer and Prof. Imam as the Dean of the Faculty of Agricultural Technology invite me to one of the speaker in today's seminar. Okay. In this presentation, I'm going to deliver this presentation with the title Advance in Supercritical Technology Extraction. Okay. This title related to the increasing demand for food, medicine, pharmacy, and cosmetic product. Okay. Dear participants, this presentation content include the first about the supercritical fluid in general, and the second, the application of the supercritical fluid, and the third, the experience of planning, building, and testing supercritical reactors, and the fourth is the prospect of semi-continuous supercritical reactors. Okay. In discussing supercritical fluid, the thermophysical properties on fluid are important information, and these properties are presented in the first diagram as in this figure. Supercritical fluid is any substance at a temperature and pressure above its critical points. Yeah. Commonly used supercritical fluid are CO2 and water. In the first diagram, there are four phases, namely solid, and then gas, and the liquid, and the supercritical region. In the supercritical phase, a fluid can be in the form of a liquid or gas, so without any boundaries. And this condition is important information about supercritical fluid. Okay. Dear participants, in the following table, we can see some example of solvent along with the value of molecular weight, critical temperature, critical pressure, and critical density. From this table, we can see that critical temperature of the solvent varies greatly. Methane is the lowest, for example, and water is the highest for the critical temperature. I would like to show the physical properties of supercritical fluid. In this slide, you can see many physical properties of the supercritical fluid. Excuse me. And I would like to show the physical properties of the supercritical fluid, which can help in many processes, such as extraction and synthesis of nanoparticle, and also biodiesel production. Okay, excuse me. The following, we are going to present some application of the supercritical fluid. This figure show the, that the supercritical fluid can be used for various processes. And in this presentation, we will discuss several use, are widely used in bioprocess technique, such as extraction, nanoparticle synthesis, micronization, and then the synthesis of biodiesel. Okay. From the supercritical fluid properties, we can use it to extract certain component from the product, especially biomass product. The basic procedure for extraction with supercritical fluid is follow. The first is the partition of volatile substance by contacting supercritical fluid with feed material. Second, soluble material dissolved into the supercritical fluid. And then the extracted component then separated by changing pressure and temperature. And finally, the supercritical fluid recompressed and recycled. And then from this process, the solvent as supercritical fluid can be reused and will be not disturb the environment, and it is efficient in the use of the material. This. The following figure show the extraction process using supercritical fluid, and then the essential part consists of extractor and then separator. We use CO2 tank. We supercritical fluid, we use CO2, and then this is in general scheme of the system of supercritical extraction. And we also see here, supercritical fluid extraction has several advantages. It is relatively rapid for low viscosity and high diffusivity of SGF, easily recoverable by changing pressure and temperature, and the non-toxic solvent leave no harmful residue, can be selective by controlling density, and then the last advantage, high boiling components are extracted at relatively low temperature. And then it can be used for the extraction of several types of products, such as food and flavoring industry, for decaffeification of tea and coffee, extraction of essential oil, aroma material from spices, etc. This is and we can see here, there are several extract products using supercritical fluid extraction that have been marketed with health benefit and high economic value, such as the essential oil of lavender, essential of ginger, and essential oil of basil. Okay. Ladies and gentlemen, in this table, we can see some result of essential oil produced using supercritical fluid extraction. Roasted peanut need CO2 as a solvent on temperature equal to 50 and pressure equal 9.6 megapascal. As optimal process condition, and the other material also need specific optimal condition like macuna, aterima, cafe. So from the table, this table, we can make conclusion that in the research of supercritical fluid, to determine the optimal process for every material. Okay. Also, there are many research, supercritical fluid extract can also be used to reduce fat content. For example, for cheddar and Parmesan cheese, we can minimize the fat until 51%. And then for flax flour from sticky rice, pandan leaf for pharmaceutical material, ginger to pharmaceutical material, and black pepper use it for medicine material. And the other one, we can also for aromatherapy, Eucalyptus globulus, leaf of the Eucalyptus globulus for aromatherapy, and then lavender also for aromatherapy. Okay. The second application of supercritical fluid is used to form nano-sized particle. There are several records for the formation of nanoparticle as follows. The first is supercritical fluid precipitation technology produce a particle with nano dimension. Supercritical fluid provide a number of ways of achieving this by rapidly exceeding the saturation point of solute by dilution, depressurization, or combination of these. The third, this process occurs faster in supercritical fluid than in liquid, promoting nucleation of crystal growth and yielding very small and regularly sized particles. And then recent supercritical fluid have shown the capability to reduce particles up to a range of 5 until 2000 nanometer. And this technique is locally used in pharmaceutical industry. We are going to micronization. This is a supercritical fluid micronization is one of the modern technologies. And there are three kinds of technology to produce micro-scale products. We can give name RES, rapid expansor supercritical solution, and then SAS, supercritical anti-solvent, and PGSS, particle from gas saturated solution. RES method. The explanation of the RES method is as follows. The SGF is used to dissolve the solid material under high pressure and temperature, thus forming a homogeneous supercritical base. And the second, the solution is expanded through a nozzle and small particles are formed. And then, at the rapid expansion point, right, at the opening of the nozzle, there is a sudden pressure drop that forces the dissolved material to precipitate out of the solution. This is important information. And the last, the crystal that are instantly formed enclose a small amount of the solvent that, due to the expansion, change from supercritical fluid to its normal state, usually gas, thus breaking the crystal from inside out. At the same time, for the reduction of size chip while forming and breaking crystal collide with each other at the vicinity of the nozzle. The particles that are formed this way have a diameter of few hundred nanometer. And we can see here the instrument for rest method. Yeah. We use SGF, CO2, and then we also need a fluid reservoir, and the last one is the RAS rest chamber. Yeah. We have a nozzle here, so the expansion nozzle can create the micrometer of a particle.
Okay, thank you very much. First of all, I'd like to express my sincere gratitude to the organizing committee of the 6th ICGAB to offer this opportunity of keynote. My talk, the title is Potential of Thermotolerant Yeast and its application for high temperature ethanol fermentation. This high temperature means around the 40 degrees Celsius. But if you use Saccharomyces cerevisiae, the temperature should be kept around 30 degrees Celsius. So about 10 degree higher temperature fermentation. Over 20 years, we organized 3 international core programs with Asian countries focusing on tropical microbes and their application. In these core programs, there are 250 researchers from the 70 universities and the 7 countries, and including the Indonesian scientists. In this programs, University of Brawijaya was a core university. As you know, global warming is a worldwide issues of this century. We believe that the application of tropical microbes can contribute to solving some issues related to SDGs. We can apply thermotolerant microbes for fermentation and biodegradation, bioremediation due to its the resistance to heat and the many stresses. Especially the high temperature fermentation has several merits. That is reductions of cooling cost and prevention of contamination and saving hydrolysis enzyme cost and the easy operation. The thermotolerant yeast in this topic is Cucurbitacea malicianus. That is generally recognized as safe and non-GMO and resistant several stress accumulated during fermentation and applicable for utilizing cellulosic biomass. This yeast compared to Saccharomyces cerevisiae, thermotolerance and using various sugars, including xylose. In addition, this yeast show the high growth rate even at high temperature and efficient protein productivity. So we completed genomes 2015 and found the many the hexose pentose transporters as we expected, including the xylos. And also we found the 30 genes shared with the thermotolerant Hansenella polymorpha, but not shared with some sensitive Chlorobromyces lactis. So these genes may be required for survival at high temperature. Also, we found the different metabolic flow at 30 and 45 degrees Celsius in this yeast. And this shows the resolved oxygen levels. You can see the different, this is 30 and this is 45 degrees Celsius. Consistently, the NADH oxidase activity is high at 45 degrees Celsius. And as we expected, high temperatures, cellular or mitochondrial ROS, this is reactive oxygen species level, higher than the 30 degrees Celsius. And the glutathione levels lower at 45 degrees Celsius. And interestingly, NADPH levels were higher at 45 degrees Celsius. And also, we notice the mitochondria morphology is different between 30 and 45 degrees Celsius. At 30 degrees, you can see fusion form, but the 45 show the fission form. To understand the further metabolic change, we try the transcriptome analysis. We incubate cells at 30 degrees Celsius for 4 hours and then shift up to 45 and the further incubate 30 minutes for 2 hours and the isolate RNA and subject it to RNA-seq. So this shows the some of the data, the glycolysis pathway and pentose phosphate pathway. After immediately the temperature up shift, the expressions were reduced. You can see in the glycolysis pathway, but the pentose phosphate pathway, for example, ZWF, nearly constant. And especially the FPP1, this is needed for gluconeogenesis increase. So, looks like the glycolysis down-regulated and pentose is nearly constant, and then maybe the cycling this pathway. And also, we confirm this transcriptome analysis by the enzyme analysis, and nearly consistent data was obtained from the enzyme activities. So we think this pentose pathway is main pathway at high temperature and then produce NADPH. So this is consistent with our previous data at high temperatures, NADPH levels higher. And the this is like models. The high temperatures pentose pathway, like cyclic pathway, produce NADPH and remove ROS, which is accumulated at high temperature. So, however, we needed the Chlorobromyces marcianus wild type to improve the more resistant to various stresses, and also improve the utilization ability of cellulosic biomass. This shows the the earlier obtained mutants, robust mutants, which were isolated under various stresses. So there are two mutants, KMR1042 and 118, both show the resistant at higher temperature, you can see, compared to wild type, and also resistant to the high concentration of glucose and the high ethanol, and also hydrogen peroxide. So liquid culture also show the temperature resistant compared to wild type. But in addition, these two mutants show the stronger sedimentation, which is beneficial for the recovery of the cells for next fermentation. Recently, we developed the laboratory adaptation technologies, which is very simple and very efficient. The procedure we call the RLCGT. This method, this is repetitive long-term cultivations with gradual increase of the temperature. So we tested 10 tubes and then obtained the 4 mutant. So very efficient. And obtained mutants show the resistant, the acetic acid and the low pH, and also the ethanols and the fluorophore, hydroxymethyl fluorophore. We also, this mutant, actually we obtained the 4 mutant, and that show the higher fermentation abilities. You can see here the wild type is stopped the fermentation here, but the mutant use glucose mostly at 40 and 42 degree. When we use 16% glucose, and the produce ethanol higher than the wild type. We use this technology for improvement other yeast. This is Candida tropicalis. In this case, we try the 4 tubes and obtain 1 mutant. This also shows robust resistant, robust mutant phenotype. So the resistant to high glucose, high ethanols, fluorophore, and hydroxymethyl fluorophore resistance. And also, this strain can use xylose. So compared to wild type, the mutant show the use more glucose and produce more ethanols, and also produce ethanol from the xylose. As you know, when we utilize the cellulosic biomass, we need expensive cellulases. So there are 3 typical, the main cellulases, like cerobiohydrolase and glucanase beta-glucosidase. Especially this beta-glucosidase degrade cerobiotes. So Trichoderma rhizae, this is well known, the cellulose producing fungi, but this fungi produce less the beta glucosidase. So the commercialized cellulases actually mix with the Trichoderma rhizae enzymes and other enzymes, like aspergillus. So if we can make the this beta glucosidase by the yeast, we can make the easy or economical ethanol. So we try to mutagenize the equilibriumyces to obtain the cerebiose fermenting mutant, because we know the putative genes in these genomes. So we tried 15 times UV treatment, and then finally obtained the cerebiose fermenting mutant, and especially from the SY13. After that, we screened the mutant with 2-deoxyglucose as a glucose analog. You can see cerebiose utilizations, actually assimilation increase here, and then produce ethanol. But unfortunately, glucose assimilation is reduced. So we analyzed the genomes and compare to this mutant, and then 13 to 14s very enhanced the cerebiose assimilation ability. So we found the 4 glucose transporter, 3 the glucose transporter. These mutations maybe stop the glucose, and then stop the glucose repressions, and then produce the beta glucosidase. So we try to do the co-culture of DMKU3142. This is the wild type, which can utilize glucose, and SY15-2. This cannot use glucose, but can use cerebiose in the glucose and cerebiose mediums. You can see the can use glucose, cerebiose, and then produce the ethanols. So now we can do the economic conversion of the cellulosic biomass to ethanols using the Proboscis wild type, the mutant strains, and T-Rhizae from the glucose to ethanol. So if we consider the reductions of carbon dioxide emission to produce ethanol, in Japan we have only the household or corporate waste or food loss as a raw material. And also we should consider the equipment and also transportation of raw materials and then product. And we needed the further innovative technologies. For such a purpose, we tested the pilot, semi-pilot by 2 the project. One of the project, that is Asia Joint Research Project. The member is Indonesia, Thai, Laos, Japan. We are supported by the district dicty, and then convert biomass in Asia to bioethanol, acetate, lactate. So this shows the general ethanol production process, but especially second generation biomass, the cellulose cost is about 40% of the total cost. So we needed the new technologies. So this shows the new technology for bioethanol production. So at high temperature, we can do fermentation, distillation together under low pressure. And after simple distillations, we can further concentrate it by membrane separation. The ethanol we can use into the car after conversion to hydrogen. And also, we developed the direct conversions, very low concentration, ethanol to hydrogen to electricity. So this is a recent our project with a Japanese company, and this is a low carbon technology research and development, RE100 distributed power supply utilizing food processing waste. So the food waste from the Nissin holding, and then we try the high temperature fermentation here. And then some is go to membrane separation, and then make the high concentrated ethanol for starters of the engines. And meanwhile, the ethanol low concentrations go to the engines, and then the converted hydrogens and then electricity. So this is our centers. We have the three groups, and focusing on some tolerant microbial resources. If you have some interest, please come to do some collaborative work. So this is acknowledgement. Okay, thank you for your attention.
Thank you. I'm going to share my screen. So, are you able to see my screen?
Yes. Is it clear?
Okay. Good morning. Thank you for the invitation to give the talk, and in particular, I would like to thank Hendrix, Yusun, and Marianne, who are my previous colleagues at the University of Western Australia. And of course, I would like to acknowledge my PhD supervisor and master supervisor for their training and support. And I would like to thank all the research funders and industry partners to provide the financial support to do all the research. My topic today is about hydrogen and hydrogen carriers production from biomass and biomass waste. The reason I'm talking about the hydrogen today because the hydrogen is back. This is not the first time to talking about hydrogen as renewable energy or low carbon fuels. In the last 30 years, in 1970s and late 1990s, there are two waves of hydrogen energy. But that was mainly driven by the economics and energy crisis. However, this year and this time, we are talking about hydrogen as a low carbon fuel or zero carbon fuel to decarbonize our society, simply because are driven by the environmental issues, the climate change. In that sense, it looks like there's no way to go back, and it's going to play a very significant role in our the whole energy mix in the future. And the UK government is very ambitious to drive the hydrogen energy in the last few years and nowadays. provide like 1 billion pound what is called net zero innovation portfolios and target to reduce like almost 80% of CO2 emissions by 2035. And hydrogen is one of the key players in decarbonizing the heat power and of course the propulsion thermal in the transport. It is estimated to produce like 250 to 460 terawatt in hydrogen by 2050, and 50% of the commercial transport is going to be powered by hydrogen, particularly in the jet fuels. For example, you can use liquid hydrogen, or you convert hydrogen to sustainable aviation fuels. Most importantly, according to the recent report, what they want to use hydrogen is from different resources. At the moment, is mainly from methane steam reforming, and of course, the water electrolysis is going to play a significant role now, and it's flying. But it is estimated about still like 20 to 45% of the hydrogen is going to from the biomass. And of course here biomass is not the current biomass or agriculture waste. The biomass we're talking about is the energy plant. Of course what we have, the agriculture waste, the food waste, any waste can be used for the hydrogen production, but the feedstock is not sufficiently to produce enough hydrogen. So I just give you the overview of different hydrogen production and the cost in the current market. In the current commercially available technology for hydrogen is mainly the steam methane reforming. Basically, is the steam reacted with methane. This is widely used in the hydrogen production for the oil refining and use hydrogen for ammonia production. And this is quite cheap, but recently, because of the high price of methane and the process produce carbon dioxide. And if we want to capture the carbon dioxide, and the cost will goes up. And that's why the levelized cost of hydrogen production now is around, £250. And of course, I believe it's going to be high because this figure is from 2019, and particularly because of the Ukraine and the Russia war, and the price of methane goes up, and in the Europe, and the price of hydrogen production, of course, will goes up as well. And then we're talking about the water electrolysis, and because of the low scale and the high cost of the renewable electricity, the production cost of hydrogen is much higher than the current methane forming. And the people try to modify the current methane reforming process. For example, you can burn some of the methane to provide the heat for the process. What we call is autothermal reforming process. And of course, we are working on using the calcium to capture the CO2 simultaneously during the steam reforming, which I'm going to give you a very detailed description of the whole process. And we try to reduce the cost. And of course, in a biomass gasification, pyrolysis for the hydrogen productions, and with the carbon CO2 capture, so is another way to produce hydrogen, and the cost is very competitive to the methane reforming process. And of course, in the research areas, we're talking about biological ways, we're talking about the catalysis produce hydrogen, but the technology readiness level is still low and in the research discovery stage, and the cost, of course, is very high at the moment. So I'm going to give you a brief overview of a few technology we are developing at Komunitas University and some of the technologies I was involved. So one of the projects we are working on is called HYPA, is a hydrogen production from methane. Of course, that can be adapted to use the biomass waste. So this is supported by the Department of Business, Energy and Industry Strategy in the UK. So the whole process is about to integrate the steam reforming with the carbon capture. Conventionally, and you have steam reforming to produce hydrogen and the carbon dioxide. Afterwards, and after treatment, you use calcium to capture the carbon dioxide. But in this process, we integrate the two processes together. Basically, you put calcium, the lime, into the reactor with the steam and water together, and during the steam reforming process, and the CO2 form is going to be captured by the lime and turn lime into the limestone. And with the limestone passing through passing the cyclone here, and the hydrogen will be separated, and the limestone, calcium dioxide, will be circulated back and go to another reactor here. And this was heated by the residue off gas, and the limestone, when the limestone is subject to the heat, the CO2 will be released and separated, and the lime will goes back to the process. So basically, the concept of this process is to integrate the conventional methane reforming with the limestone capture process to capture the CO2. So the process is based on the current in the GTI, the hydrogen gasification or steam reforming process. And we just try to add the lime into the system to capture the CO2 simultaneously. So we try to design and construct a 1.5 megawatt pilot plant in the university. And this is the site that we try to build. And it is expected the whole system, if it can be successfully demonstrated, is going to reduce like 50% of the capital cost and to achieve 20% cost of the hydrogen production. So another technology I'm going to talk here is the biomass waste pyrolysis process. So basically, if you have the biomass stock and you can process it using like supercritical extractions or sonic chemistry to extract value-added products, and then you subject to the heat treatment, what we call is pyrolysis, is in the inert environment and heated up to like 600 degrees C or 700 maximum. Pyrolysis process will produce gas, biochar, and of course you have oil. And the pyrolysis gas here you have carbon monoxide, hydrogen, and of course contains methane and carbon dioxide as well. And after gas cleaning, separation, you can produce hydrogen. And biochar can be used as a soil conditioner, or you can use it as a fuel, and you convert biochar into high-value carbon materials like activated carbon for the solvent. And the pyrolysis oil, you can burn it to provide heat for the pyrolysis process, or you want to refine pyrolysis oil to produce other oil products. So we are working on the pyrolysis process because the pyrolysis is different to the gasification. The gasification would require a very high temperature, basically is more than 900 degrees C to produce syngas. And that is only economically viable at a very large scale. Okay, but the biomass waste has a nature of it being scattered at a small scale. So pyrolysis is particularly suitable for the small scale, the biomass waste production and processing here. So the way to use the pyrolysis gas, what I'm talking about today is hydrogen, but of course you can burn hydrogen or the pyrolysis gas in the gas engines for direct heat and power generation. So that's why the whole concept is you can suit for different applications, hydrogen, bioenergy, and if you're chasing biochar, that's all fine. So this is, the pilot scale demonstration is the kiln reactor, which can produce like a 100 kilo of biomass, woody biomass, and to produce syngas. And as you can see, the hydrogen concentration in the syngas, in the gas, what we call pyrolysis gas, can be reached like 30 or 40% at a relatively high pyrolysis temperature. And one of the concept here is we try to use biochar because biochar is an in situ product. And we try to use biochar as a catalyst to further cracking the pyrolysis oil and to enhance the pyrolysis gas production, particularly to chasing hydrogen yield and the concentration in the pyrolysis gas. And we have done some lab scale fixed bed reactor to use the biochar produced in the process and to further enhance the oil, to process the oil to enhance gas productions. As you can see, overall, the gas production can be improved. In some of the cases, can be doubled in terms of the total yield. So that the previous, methane reforming and biomass pyrolysis for hydrogen productions, what we're talking about chasing is hydrogen. However, I have to make it clear here that hydrogen as an energy, as a fuel, has a challenge in the current form, simply because of the hydrogen has a very low volumetric density. And of course, hydrogen is very hard to transport and store. And this, if we want to use hydrogen as a fuel, and we have to think about energy density. So this figure just to give you the indications of different fuels. Conventionally, we have diesel, we have biodiesel, we have petrol, and of course we have jet fuels. And both the volumetric density and the gravimetric density are very high. And if we talk about the hydrogen here, of course, is very clean, but the volumetric density of hydrogen is extremely low. That means for a same size of the tank, you can't hold much, energy. So that's why sometimes the hydrogen at the moment, the most easiest or the reasonable practically way to use hydrogen is to use a carrier. You convert hydrogen to something. In this case, what we are chasing here is try to use like ammonia and methanol as a hydrogen carrier. You can convert hydrogen into methanol, into ammonia. The reason to use ammonia and methanol as a hydrogen carrier, previous slide, just to give you the energy density, so they are reasonably comparable. It's not high enough compared to the current conventional fuels, but also it has a reasonably volumetric and gravimetric density. Most importantly, both ammonia and methanol, they're already in the large production and commercially available. They enjoy the very success and mature infrastructure, and they can be easily stored as a liquid fuels. For example, ammonia, you simply compress ammonia to like 9 bar and at atmospheric temperature, so it will be a liquid. Methanol is already liquid anyway. So it's a very easy store and transport. And they relatively have the high hydrogen concentration, and ammonia has like 17.6 hydrogen wet percentage, and methanol is a little bit lower, but still reasonably high. So, for example, the pyrolysis technology I just mentioned before, you have the biomass go through the pyrolysis process, and you have using the biochar as a catalyst to further cracking the tar pyrolysis oil to produce syngas, and the syngas after cleaning, and you produce hydrogen carbon monoxide. As I said, hydrogen is hard to use, and then you can add a methanol synthesis process to convert hydrogen to methanol. And methanol can be easily transported and to wherever it's needed. So this is the concept that we are working on. For the methanol, so of course the current methanol production, you have copper, zinc, aluminum oxide as catalyst, and you can produce different concentrations of copper and the zinc in the process, try to tune the compositions of the catalyst to suit different applications, particularly for the biomass pyrolysis, simply because biomass in terms of the concentration varies significantly from one location to another location. That's why we need a catalyst to be robust to handle pyrolysis gas with varying compositions. So these are the pilot plant that we are working on. You have the kiln reactor to build the pyrolysis, and you have the in this case we are working on the woody biomass, and you shred it into all biomass powders and put it into the kiln reactor and to produce syngas and add a methanol production plant there. The same value process for ammonia as well. So for ammonia, of course you can use biomass or waste. At the moment, you can use natural aniline feedstock, and you go through the pyrolysis gasification reforming process to produce hydrogen, and the hydrogen react with nitrogen from air to produce ammonia. At the moment, ammonia is the largest fertilizer produced feedstock in the agriculture, and what we are trying to do is, can we use ammonia as a fuel, a hydrogen storage transport fuel? So in Japan, for example, they are very ambitious to use ammonia as a fuel. They already demonstrate ammonia in the gas turbines. And in Australia, they try to develop ammonia energy. Basically, they have abundant solar energy, and they use solar panels to produce hydrogen and convert hydrogen to ammonia. Then they ship ammonia to China, Japan, Korea, India. And when they receive it, they can directly use ammonia as a fuel or convert ammonia back to hydrogen to use it. So what we have done before is we tried to use ammonia as a fuel, and we studied the basic combustion characteristics of ammonia and the NOx formation. The use of ammonia has a challenge here is it burns very slow compared to methane. The flame speed of ammonia is only 1/5 of that methane. That's why it's very hard to burn. And also, ammonia contains nitrogen. So during the combustion process, it may form NOx. And that's why the technology development now is trying to increase the burning velocity. Basically, is to make the burning more effective, and of course, in the simultaneously try to reduce the NOx emission. And of course, you can directly use ammonia as a fuel cell, like hydrogen fuel cell in the solid oxide fuel cell, the high temperature solid oxide, to directly convert ammonia to electricity. So there are lots of research is going on in the worldwide in try to use ammonia as a fuel. So this is just to give examples of what we are doing here. In a nutshell, so hydrogen is very, very active in the UK, I believe in the world as well.